The main objective is to learn how to implement mesh motion in OpenFOAM. Crashed, and what we are seeing is the previous run, but clearly the mesh quality degraded. You can also see that how you should define things. So before diving into the setup of moving mesh, let's first set up a simulation in OpenFOAM. In order to do so, there are various ways in which we can create a mesh and then we can set up a simulation. Here we are going to use Gmsh to create a geometry as well as the mesh, and then we are going to convert the Gmsh mesh into the OpenFOAM compatible format. Then we are going to set up a simulation which accepts a dynamic mesh. Let's go to the OpenFOAM website and see that what are the compatible solvers that allow moving mesh. In the OpenFOAM website, if you go to this particular web page, you'll see that there is a compatibility matrix. Here you will see the list of solvers that are there in OpenFOAM and what all other options they allow. For example, in IcoFoam, you can have a transient simulation, but you cannot have compressible simulation, you cannot have turbulence, as well as you cannot have a dynamic mesh. For our case, we are going to use this particular solver which allow a transient simulation, allows turbulence, and allows dynamic mesh. We are interested in dynamic mesh and therefore we are going to use this. Let's go to temp and create a directory called flow past square. Let's go here and open Gmsh, and in order to create a script, as you may already know that you have to create at least one point. Let's create one point and another and close this. If you look here, you'll see that there is a file which is created. We'll rename this to something like FPS Geo and then edit this. Here you can add all the points which are required for you to create the geometry. The first three parameters are the XYZ coordinates and the last one is the mesh resolution. We are going to use these parameters. We are going to use two mesh sizes. This mesh size is for the outer domain boundary and this mesh size is for the inner square cylinder. And then these are how you can write a comment. These are the 4 points. This is the lower leftmost point. Similarly, all other points. For all of them, the z coordinate is 0 and the mesh size we have chosen is 1. In a similar manner, you can add the 4 points which belongs to the square cylinder. Here are those 4 points. Once this is done, you can close this and go to Gmsh and open this particular script. Once you open this, you will see that all those points which you have created are here. You can connect them using this user interface. You don't have to write it manually. However, you can always write this manually. You can create surfaces by selecting consecutive lines like this and pressing E. Similarly for next one and this one. Now you can create a 2D mesh. See that a 2D mesh is created, but for OpenFOAM it requires 3D. In order to create a 3D mesh, you can extrude the mesh along Z and create only one mesh layer and extrude the mesh as well. Then select all these mesh elements and press E. You will see that there is a volume that has been created, and if you click 3D, you will see that a 3D mesh is also created. Next, you should label all the boundaries. In order to label, you can go to physical groups, then you can add a surface. So I'll add this as inflow. Similarly, outflow for this one, and these are walls, and this is square, and the last one is front and back. These are along the Z direction and not going to affect the simulation, but still you have to assign some label to this. You should also assign some label to the volume. This is interior. You can export this as sixDoFMesh, and make sure you choose a Gmsh extension, and then here make sure that you select a version 2. You can also check that everything we have done is added to the script, including these labels. In order to set up the simulation, we need to copy the folder structure which is required for OpenFOAM simulations. You can choose any of the simulation. I always choose cavity example because this has the bare minimum which is required for any simulation. Copy everything here. You will see you have everything. Now use Gmsh to foam command, and then right here fps.mesh. You will see that this has created. You will always see this particular warning, but you cannot ignore this particular warning. When you open this in ParaForm, you will see that it has all these labels that you have created. Let's see those labels. This is inflow, outflow, square, and wall, and there is a front and back. If I switch it on, I can see the front and back walls as well. One more thing that you should notice, that in the polymesh file you will see all the labels that has been created. Usually they are all created as patch. You have to change this to whatever type you want. I want this as a wall and square also as a wall. Let's set up the simulation for PimpleFoam solver, and this will be a transient simulation. Let's open VS Code and open this folder. Once you open this in VS Code, you will see all these files. First of all, we have to set up the boundary condition. You can set up by first copying what all boundary conditions you have. Let's copy those from here. We don't need these. For front and back, this is an empty kind of boundary condition. Square is a no slip wall. We want 0 gradient here for pressure, and here as well we want 0 gradient. For outflow, we should have a fixed value which should be equal to 0, and the inflow should be 0 gradient. Once this much is done, you can do the same thing for velocity. For velocity, front and back same as before. The square is no slip and the wall is slip wall. The outflow should be 0 gradient and the inflow should be fixed value with value equal to this. We should also set the viscosity. Viscosity we are setting to 0.01. We can calculate the Reynolds number, which is 2d by nu. Our d is 1, the length of the square, which we can see here. It is 4.5 to 5.5. That means it's equal to 1. ud by nu is the Reynolds number. Nu is 0.01, so therefore our Reynolds number is 100. We can now make changes here. We'll have a PimpleFoam solver here. We'll keep the same time step, but we'll change the end time to 100 and write interval as 1 in the FV scheme. Even though we are not going to use any turbulence viscosity here, but still for PimpleFoam we have to define that how we are going to solve for the viscous term. So that's why we need, since we are using a triangulation, we can change this to corrected and this also as corrected, and there is no need to change anything else here. Then for the solvers, we have to make some changes. For example, here we should have a pcore, which is required for PimpleFoam solvers. You can use this particular symbol to add two variables that are using same solvers. Here also we will have pcore final. This one we should change to pimple. Now we can try to run this. Let's run PimpleFoam. So here you have a patch which is defined as a patch, but the constraint is empty. This is the problem. We have a boundary condition here as empty, but this is defined as a patch. So you can only have a patch when it have some boundary condition. If it does not have any boundary condition, it should be assigned as type empty in the boundary. So let's rerun this and see if it runs. we still have one more problem. In the transformer model, there is no model found. In PimpleFoam, you cannot just define this. You have to have a transport model here. We can write transport model as Newtonian, and again try to run this. The turbulence properties are not found. Even though we are not running a turbulence simulation, but still it requires its properties file. We'll copy this and create a file with this name, turbulence properties. You can see that it is a laminar simulation and everything else is not required. Let's rerun this. U final is not found. Again, let's go back to the solver. Here you should have a U final as well. Let's add that. Make sure we are changing the right variable, and again rerun this. We can see that it is running fine. Let's run for some time and then we'll post process this. We'll just look at some kind of vortex shedding. Let's wait. Let's look at the results. Here you can see the shedding is happening. Now we'll use this simulation and we'll see that how we can move this body or move this entire domain and run simulations in OpenFOAM. The main objective is to learn how to implement mesh motion in OpenFOAM. Let's get started. First of all, in order to find out that how we can set up mesh motion in OpenFOAM, let's first look at one of the tutorials that are already there in OpenFOAM. Remember that we cannot have a mesh motion simulation in IcoFoam. Let's look at wing motion 2D PimpleFoam. Here we have a dynamic mesh dict. Let's copy this particular file to our constant folder. Along with this, for all kinds of mesh motion, we also need one more file, which is inside the 0 folder. You should have a point displacement. Let's copy this to 0 point displacement. Once this setup is ready, let's open the dynamic mesh dict. We have so many things here, but the first thing to notice here is that we have to define that which kind of this dynamic FV mesh we want to use, and then there are various other parameters. We'll see how we can find out in the source code that what is this and what are all other things. The second thing is this: in the 0 folder you have point displacement. So the point displacements tells the solver that where we want it calculated and where we want it to figure out on its own, and where we want a fixed value. We don't want the mesh to move there at all. Let's go to the source code of OpenFOAM. Let me open that. First of all, this is our OpenFOAM source code, and here we can see all the solvers, and in the utilities, in mesh, in manipulation, we have methods to move the mesh, which is move dynamic mesh. We have to find out that when we are using one of them, how do we know that what are the parameters that are involved. First of all, this is the bare minimum that you should know, that what kind of file you have to write. Unless there is an example, it is very hard to find out that what kind of file you have to write. This much is bare minimum. You should get this from one of the tutorials. Then you have to go to DynamicMotionSolverFvMesh. Let's go to the DynamicMotionSolver. We'll go to the source, and here we have a dynamicFvMesh, right? And inside that we can see we have a DynamicMotionSolverFvMesh. Let's look at this file and see what it requires. This dynamicMotionSolverFvMesh file, in the header file, it requires a motion solver. Therefore, we see we have a motion solver here. And in the .c file of this corresponding header file, you can also see that how you should define things. It is saying that this has added to the runtime selection table that you have to define this dynamicFvMesh, which is here. Then let me show you that how we can find how many types of motion solvers are there. You can go to the terminal, and let me go to the source code. Right, this is the source code, and let me go inside this as well. Inside this, you can use this particular program in Ubuntu environment, you have this particular program which is called ripgrep. You can install this, very powerful tool. Using this, you can find that wherever motion solver is written, it will point out where it is. These are all the locations where motion solvers are defined. You can see you have a 6DoF rigid body state. Then you can have an extend displacement mesh mover. You can also have a velocity component Laplacian. You can have displacement SBR stress FvMotion and various other. Wherever this motion solver is defined, like this, let's go to one of the motion solvers. Let's say I want to go to some of the motion solvers that are defined in dynamic mesh. In the dynamic mesh, you can go to the motion solvers, and here you will find component displacement. This is one of the motion solver. You can see this is subclassed out of this motion solver, and whenever you use this particular solver, you have to define like this: component displacement motion solver. And these are all the inputs that it requires. It requires the component name like XYZ, the direction, component to solve for, and then the reference point field of this component. There is one more kind of mesh motion here, rigid body mesh motion solver. You can see what is the type. You can see here, this is the motion solver, and this require a motion solver function. In the solid body, we can see here we require a solid body motion function. Whenever we use a motion solver as solid body, we have to use a solid body motion function. You can see that how you can go through these source files to figure out that what it requires. You don't have to entirely depend upon the tutorials. We'll use this particular example of flow past a square cylinder, and we'll try to move the mesh around the cylinder such that it oscillates or do some kind of funny motion, and we'll do the minimal amount of changes that are required to get what we want. Let's do that. Let me remove everything else here, and I'll add things one by one whenever we require. Let me first try to do a rigid motion. The rigid motion is something when you want the motion to a certain patch of the mesh. Here you have to select in the motion solver. Inside this, you have to select a rigid body mesh motion, and after that you have to select a solver. This is how you define the libraries. Inside this, you have to select the same thing, which is rigid body motion. Let me select a motion solver, which is rigid body motion. In the boundary fields, in the front and back, we'll keep empty. For the square, we want it calculated. We want it to move according to whatever we are setting. The wall, we want fixed value. Let me copy it from here. Here we want fixed value, and then in the outflow we want fixed value, in the inflow we want fixed value. Let's remove everything that was there before. We also need to set boundary condition for this. When this is moving, we cannot have this kind of a boundary condition. We should have a moving wall velocity with the value equal to 0. The velocity will be set using the mesh motion. Now let's run this. It is asking that there are no bodies defined in the dynamic mesh state. That means in the dynamic mesh state, it requires bodies. Let's see how we can define bodies. We have to define bodies, which is a square. The type we want here is of type rigid body, and the parent is root. We have to define the parent. For example, if we want a body which is moving and it should move with the parent, the body is kept on a disk and the disk is also moving, so it will move locally according to whatever motion we are setting, but it has a parent which will follow as well. Now we have to set some inertia and velocity and various other things. Let's see what various other things we require. We'll go to the source code again. Now we'll look at this. We are doing a rigid body motion solver. We'll go to a rigid body motion solver. Let's go to that. Here we have a rigid body motion solver. This requires all these, and there's a mesh motion which requires this. It requires the inner and outer, how it is going to morph. Let's set that as well. Here it requires the patches, and it is subclass from displacement motion solver, which is not here. Let's go here, and probably this will require bodies motion solver, this rigid body model, and this has a friend class which is rigid body solver, which we just saw here. And in the rigid body model, you will see all these bodies, the body IDs, the joints which are required. So what we are going to do now is we'll set these basic things which are required in bodies. Let's see what are required in the bodies. In the bodies, we require just the name and whatever is required in the rigid body inertia, which is the mass, the center of mass, and inertia. Let's set that. So the inertia should be symmetric. We just require 6 values. Let's set any 6 value, 0, 1, 0, 0, 1, 0, 1, because this is not a real simulation. Let's set mass equal to 1 and center of mass equal to this. Our center is at 5, 5. We'll set this to say 4, 4. And now for the bodies, we also require joints. Let's see what are joints. We have joints here. These are all the joints. Joints are of type composite and floating. These are all the values. This is the joints.h file, and these are the revolute. These are the prismatic joint. We just need the revolute joint of type composite. Let's see what is composite mean. This is the prismatic joint for transfer along the specified arbitrary axis. Let's do that. We want to set this as type composite with joints as type RC. If this is done, we have defined the joint, then we can come out of it, which is the rigid body model. Let's come out of it. This is the rigid body motion. For the rigid body motion, we can set a damping as well. We can switch this as well. Let's go again to rigid body mesh motion, which is this. We have a rigid body motion model. We have already set this. Then we require the row inf and row. Since this is incompressible, probably it is written somewhere here. If it is incompressible, you have to define that row is equal to row inf and your row inf value, which is 1. In the rigid body motion solver, we need di and do as well. Let's see what these means. You can go to the .c file and see what it is looking for. Di looks for inner diameter and do looks for outer diameter. You also have to define patches. So let's go back here and define these. Yeah, the inner diameter should be, let's define this as 0.3, and the outer diameter, let's define this as 0.0. Patches we can define as square. Let's see what else do we need. In here, this is of type displacement motion solver, which is here. This is a motion solver. Let's see what motion solver requires. The motion solver, it requires this coefficient dictionary and the mesh. Let's go back here and let's see how do we set the solver. In the rigid body motion, we need a rigid body solver as well. Yeah, this rigid body solver needs to be declared. Let's see what are the types here. So in the rigid body solver, we have all these kinds of solver, which is Crank-Nicolson, Newmark, and symplectic. These we should pass. So let's go back here. This should be the solver, which is here. Let's see what do we need here in the solver. Just the name of the solver. You can just go back here. You can see here that a subdictionary is required. The solver should be in the form of a subdictionary solver, and then type Newmark. Let's use Newmark solver. Let's first clean this. It won't run for the entire time because eventually when we move the body the mesh is going to distort and it won't solve everything. Now let's see. It did not move at all. Let's see what is going on. We did a typo somewhere. Here in the motion solver, it required this, which is in distance, but we wrote in diameter. Let's change this to distance. And now try running this again. Check. Again, there is some problem. Let's move these two to inside the bodies, inside the square, somewhere here, because these are the bodies that we are trying to move. And again, run this. So now you can see that the object moved, and after this it crashed, and what we are seeing is the previous run, but clearly the mesh quality degraded. So let's try changing this to some other values, for example this to 1 and this to 5, and see what will happen. Again, let me clean all the fronts and run this. While this is running, we can also check that what other parameters mean. We can see that what this transform is doing. We can go back here, the mesh motion, there is no transform. In rigid body motion, you go here, here also there is no transform. Let's look here. Do we have any transform? Yes, we have a transform here. This is a transform from the body frame to the joint frame. This is required when there are two bodies, and from the parent body there is some transformation that you require. You can see what is the format here. There are two inputs to this, which is a rotation tensor and a translation vector. This kind of initialization we are looking for, tensor and a vector. This is what we have done, the tensor and a vector. Now let's look at the results. It ran for quite a time, and let's see how the mesh distorted. See how the mesh has distorted. This kind of mesh motion does not create new mesh points. It just uses that points and keeps on moving it until it can solve. This is not the best way to solve this kind of problem. There are different kind of mesh motion that should be used for different kind of simulation. If there is only a very small amount of motion, then you should do this kind of mesh motion to accommodate that motion into your simulation. Now let's look at another kind of motion which is similar to this, but has more features. That is called the sixDoF mesh motion. You can find that here. This is sixDoF rigid body motion. Here you can look at this sixDoF rigid body motion. These are all the inputs that are required. You can see here there is sixDoF freedom motion for rigid body. Here you can form restraints as well as constraints. So restraints are in some direction. You can have springs such that the motion is not completely restricted. It just have a force in that direction, and constraint is a complete stop along that constraint. You can have different options for different kind of solvers. These are all the inputs that are required. You are required to give restraints and constraints, and all these, the center of mass, center of rotation, and various other inputs that are required, including this sixDoF solver. Let's do that. Let's modify this existing file for the sixDoF solver. In order to use the sixDoF rigid body motion, just change this to 6. You can actually copy it from here, from the solver. Copy it from here to this. This is the library name, and this same thing is the solver name as well. Now these thing remains the same. We can use the same solver as well. Now let's look at what else do we need. So we don't need bodies, but we need to define, same as before, the patches on which we want to apply this. This is square, and then inner and outer distance. Inner distance is 0.3, outer distance is 1.0. And then you can also find all these details in one of the tutorials as well. Then you also need the current orientation of this. This is required to have when you have more than one body, you should have some orientation defined. So I'll just copy the orientation which was already there, and there's some more things. For example, the angular momentum and G, these are required. Then you can also have constraints. Let's go here and first see how constraints are defined. Let's go to the sixDoF rigid motion. These are the restraints and these are the constraints. These are just a list. You can go back here first and see that how it is reading the restraints and constraints. Restraints is a subject. So as you may already have figured this out, that whenever you are asked for a subject, you have to write it like this: restraint. Inside this subsection, you can have different kind of restraints. Let's see what are the different kind of restraints. Inside this, you can have different kinds of restraints. And now let's look at linear spring. Let's use any of the restraints. We are going to use this linear spring. Now let's see how we can use the linear spring. For the linear spring, we require the anchor, reference attachment point, stiffness, damping, and the rest length. All this, and similarly we can also use other kind of spring. We'll take these two from one of the examples, but you know how you can figure this out. Similarly, you can have different constraint as well. There is this linear axial angular spring. Here you require the reference orientation and the global axis, the stiffness, and then damping. Both of these we have copied. So let me copy it here. So you can see how you can define it, whatever name you want, and then inside that you have to define what is the sixDoF rigid body motion restraint. Right? In a similar manner, we can have constraints. Let me first show you what are the constraints. The constraints are here, which you can see from here. These are the constraints, sixDoF rigid body motion constraints, which are here. You can go to any of them. For example, line, sixDoF rigid body motion line constraint. Inside this, you can see there are only two things which are required, which is the center of rotation and the direction. We'll copy these two here and now save this and run the simulation again. Let me clean everything and run PimpleFoam. Center of mass not found. Let's see what happened to our center of mass. We have not defined any center of mass. Let me also copy some other things. For example, the mass, center of mass, and the moment of inertia. These all are required when you have a object which is also moving due to the force which comes from within the simulation. For example, if it is a floating body, then this is required. Now let's run this. It is running fine. Let's wait for 1 or 2 time steps and then we'll stop. It has automatically stopped because probably the mesh has distorted a lot. So let's look at the results. There was some problem with the forces as well. So clearly you have to ensure that these are correctly configured. Let's try one thing. Let's try this, which is a bigger inner and outer, which we have tried before. Again, let's run. We can also try some other solver, symplectic, and now again let's try. So symplectic is better solver than Newmark. It is second order and it conserves the volume as well as energy. Clearly it ran for 3 seconds. Let's see if it is running for more. Yeah, so this is running fine. Now let's kill this and see what is going on. So since we had a spring kind of motion, therefore this is just moving to and fro. And let's look at the mesh as well, how it is changing. Whenever you are using this kind of mesh motion, then the motion should be like this, which is similar to what you can see in one of the tutorials where the airfoil is moved in this fashion to generate the vortices. Now let's look at one other kind of mesh motion, which is when we want to move the entire mesh. This kind of mesh motion is required when we are doing, for example, an overset mesh. We have two meshes and one of the mesh is moving. For this, we have to use some other library, which is called just the plain motion solver. Here, whenever we are writing a file name with lib and .so, then we have to use quotes. The motion solver is solid body. Now let's go to the solid body and see. In the motion solvers, clearly this is a motion solver. We have to go to the motion solvers. In the motion solvers, we have to go to a solid body. So in the solid body, we have this. We need a solid body motion function. Let's go to the solid body motion function, which we can also go from here. These are the different solid body motion functions, which is axis rotation driven linear motion, multi motion, oscillating linear motion, rotating motion, as well as SDA. SDA is ship design analysis. These are the parameters such as roll, heave, and sway, which are natural to a ship compared to other kind of motions. Let's try a linear motion first. In the solid body, we have to use a solid body motion function. We are going to use a linear motion. In the linear motion, we can go here. In linear motion, we just need to define a velocity. Velocity is, let's say, 0.100. And now let's run this. Remove all the files and run. It has run enough. Let's look at the simulation. And clearly it is moving. The entire mesh is moving with some velocity. Notice that there is no option to set up any patch. You cannot have a patch to move separately. Now let's try one more. Let's try multi-motion. In multi-motion, you can have different kind of motions clubbed together. You have to type multi-motion. In multi-motion, you can have different solid body motion functions. These are a list. You can also go here and see how it is consumed. This is a dictionary. You need a list of dictionary. In multi-motion, let's have one defined as linear, which is, again, we'll define the solid body motion function and the velocity. Let's copy this here. Similarly, we can have a rotating motion. In this, we can have axis rotation motion, which is here. And let's see what do we need here. Here we need origin and radial velocity, and both are vectors. Let me write it from here. Some origins are, and this one is axis rotation motion. Copy it from here. So now we have these two motions, and when we clean all this and rerun, let's look at the mesh, how it is moving. Clearly it is moving forward and rotating as well. These are the benefit of multi-motion. You can have this kind of motion as well. With this, now we know different kind of mesh motions that we can do. These are different kind of mesh motion when we are not creating extra points. We are on a single mesh, we are trying to move a patch or the entire mesh, and whenever we are moving the entire mesh, this can be used in flows. For example, we want to move in tank sloshing, we are going to move the entire domain with some acceleration and then suddenly stop it. We can do these kind of things using this particular mesh motion. There is one more type in this particular class where we can have a coded mesh motion. For example, we need a weird kind of motion in our simulation that we can have by coding it in. Let me show that. Here in the motion solver, since we are not going to use any library, we have to remove this, remove everything else, and then we'll have here this as coded. Whenever this is written as coded, it will require some code from you, and then plug it in a set format so that it can create files for you that will do the same thing that these dynamic motion solvers are doing. They are just creating new points from the old points. They are doing the transformation for you. We can have whatever name I want, like custom motion. For this, we have to include this particular header, which is doing the transformation. And then this is the code which I have already written. I will just explain that what it is doing. This local code contains the code which is a function which is not there in OpenFOAM. You are writing your own functions that goes in the local code. And this code part contains the particular function which is doing this transformation. This is plugged in into the part where the mesh motion is done. I'll show you that where this is going. First, let me run this. In order to run this, we will just again clean everything and do PimpleFOAM. It is creating these files, and let me show you where it is created. In the dynamic code, the custom motion, you will see that it has created all these files. These things are same as what we have in these existing files. All kinds of motion have this particular function which is doing this, which is returning the current points. This piece of code is embedded inside this particular function. We can also see any of the motions. For example, let's go to the rigid body mesh motion. Here we have this return the location from the current motion field. This is the file which is returning. You can go all the way. This is the function which is returning the transformed points. It is creating a new points and then performing the transformation according to whatever is being solved here with the help of integrator or whatever. Then it returns the points, and then eventually the mesh is moved. The same thing is happening here. In the custom code, we are using our own function which is twist column, and it is returning these new points which are created from the old points, and these are transformed points from this. So what we are doing, we are taking the original points and then depending on some angle we are moving them and then writing them back to the new points and then returning it back here. Let's see how it is doing the motion. I'll just rerun this. Now let's look at the results. Since I was trying to rotate the inlet, you can see, and with this the entire mesh is rotating. Eventually this will blow up because this is not something which is natural, but you can see that you can move the mesh and the flow will adjust according to the new boundaries. You can also see here that how with this adjustment this flow direction is not changing. It's still in this direction, which is the outlet. With this, we have seen that there are various ways in which we can move the mesh points. OpenFOAM is coded in such a way that it accommodates for it and properly interpolates. We also should always look for the accuracy, whether the expected accuracy is achieved or not. We should not blindly do the mesh motion and expect a very accurate result. With this, we'll stop this particular lecture and we'll meet in the next one. Thank you.